Okay, so hello everyone, welcome back to the afternoon session. It's my great pleasure to introduce the first speaker, José Carrillo from University of Oxford. José has worked in various areas, including PDE, numerical analysis, many particle systems, and kinetic theory. In this talk, he will give introduction to the interacting particle systems and their applications to sampling and optimization. Enjoy.
So thank you very much for the presentation and the interaction and the invitation here. It's great to be in person for the first time after the pandemic. So, so today, in fact, what I would like to do is a bit of a connection with several of the groups and communities here represented in this program. So I will put emphasis in both particle and PDE viewpoints on these new numerical methods that these new viewpoints that we introduce for optimization and sampling that I call consensus-based. Okay, so we'll see what it means. Okay, so let me explain you the story from where we came and the origin of this kind of methods. So in fact, we're in the literature, so many people are looking at the problem of consensus applied to several fields. One of them, probably the most classical one, is about opinion dynamics. People were doing in social sciences models for opinion dynamics, and probably one of them, the model that got more attention, is the so-called Hesselman and Krause model, which essentially they look like these kind of models. I mean, essentially the opinion of somebody is influencing the opinion of somebody else with certain weights. So essentially the individual I is influenced by the opinions of the others with certain weights, Aij, and this they studied several, there are several models and several variants of this to analyze the formation of strong opinions clusters around certain opinions in the whatever space we are talking about in opinions values. Okay, so this is probably one of the classical examples of this. Other one that I got interested in like 10 years ago, more than that, 12 years ago, when I was doing a sabbatical at UCLA, I started to work with Andrea Bertozzi in models for collective behavior of individuals or swarming, that it was also referred in today's K talk in the morning. So essentially what you want to do in those models is to try to explain the formation of large coherent structures formed by individuals that they move in some coordinated way. So this is essentially structures that have been seen or reported for insects, for birds, for microorganisms, have been used for artificial robots in control engineering and many other fields. And basically these models, they incorporate three regions: attraction, or three regions of interaction, some repulsion that we basically understand very well now with the social distance. So there is an area in which you don't want to be too close to others. Attraction, we are social, so we want to be with others. And alignment is when you want to somehow mimic or follow the orientation or the movement of others. Okay, so I'm going to give you two examples of these models. One that was studied quite a lot by the group at UCLA, Maria Rita Dorsonia, Andrea Bertozzi, and collaborators. Essentially, it has, you can look at it as a kind of Newton-like equations in which all the biology here is embedded in the shape of this potential U. Essentially, you want to model with U the fact that the individuals, they don't want to be too close to each other. That would be the repulsion, the repulsive part at short distance of this potential, and at large distance, they don't want. They want to, in fact, to be together. So there is an attraction. Apart from that, there is this term here that its only role is to fix a cruise speed for the individuals. What you want is that all the individuals, they move with the speed square root of half over beta asymptotically. Of course, they are Newton-like equations, so Newton has to be always in my slides. Since I moved to the UK, it's my only dog. Okay, good. So, as I said, these are the two kind of effects. Just to give you an example, that's what is usually referred as the Morse potential. And you just choose the length scales and the strengths in the right way. You can cook up potentials that look biologically reasonable, repulsive in the short range, attractive in the long range, with the choice of signs I have for the potential here. Okay, such a simple model, but there are interesting things that happen. Let me run these simulations. These simulations are just 200 random particles chosen with 200 random velocities for them. These are the arrows. And you just follow the movement of them by following the center of mass. So for this particular initial data, you have at the end this formation, what is called the flock solution, meaning that all the velocities, they have arrived to consensus and move into certain direction. All the velocities are equal for everybody. Okay? So this is what we usually call flock in those kind of models. So essentially, they have arrived to a consensus in velocity. That's the point. While here, it looks like it's more or less a bit random. In fact, if you follow the movement of the center of mass, is moving around. But at a certain point, I assure you that there is something that is happening already. And then at the end, what you have is this kind of stable configuration, which is called the mean solution. So, I mean, this just to give you an example of the kind of solutions that you can have for this very simple model. And in fact, what is important for me today, for you to make the connection and see from where I came to the idea of optimization, is to think in terms of this consensus in velocity. Okay, so in fact, one of the models that have been proposed for consensus in velocity for flux was introduced by Felipe Cooker and Stephen Smale. And it's very simple idea and very unrealistic, but nevertheless simple. What you're assuming, you are in one of the birds in the flock, and you're assuming that you are able to instantaneously measure the relative velocity with everybody else. Instantaneously. And not only that, you are so smart that you can calibrate the average that you take of those velocity differences by weights that depends on the distance. Okay. And in that case, well, the typical Cooper-Smale model is just a power law, became power law of the distance. So those that are far from you count less for the average. Okay, so in this particular problem, in fact, you can show that rigorously that for as t goes to infinity, depending on the gamma, if gamma is less than 1/2, that's what equal to 1/2. No matter what the initial data is, they will always flock asymptotically. They will always achieve, as t goes to infinity, moving exponentially fast, going into the right, into the same direction. Okay, so now let's come back to business. That was a good story after lunch. Okay, so optimization. Good. Okay, I don't have to convince you, but I have this slide there, that this is an important problem. And that there have been many people and many different viewpoints in how to try to compute the minimum of a complicated function in an efficient way. I'm listing some of the ones I know, but I'm sure I'm missing many, many of them. Okay. So let me now take as an example of those system methods, simulated annealing. Simulated annealing was essentially, from a point of view, to take advantage of the fact that you do gradient descent of that function that you want to minimize. And you are adding a noise, but the noise that you add has some variance that depends on time, and you can do some kind of optimal cooling schedule for adjusting the temperature, such a way that asymptotically, you're going to put essentially zero noise to stabilize around the minimum of this function. Okay, I think probably even have, well, I mean, that kind of thing. Okay. So you are changing the temperature in such a way that you make the temperature small, so this beta t, such a way that at the end you end up in the, well, that case maximum of the function. Okay, so, but what I would like to do, well, is to allow for irregular objective functions that you will see. And I would like to be, well, in principle, this method is not guaranteed to find the global minimum. Correct me if I'm wrong, I'm not the most recent, I don't know the most recent results about simulated annealing, how it is the result right now, but there are some advantages and disadvantages, okay, of this. Okay, so let's summarize. This is what we want to do. And just an example, if we are thinking in terms of what the theme of the also of the program is about relations to machine learning. So let's assume that we have a loss function, that we have some data, and then we're taking an average to do that. So I'm going to propose you a different kind of method. Why not to use a non-gradient method? Okay, so I'm going to assume for that, let's assume the gradient is hard to calculate. Okay. So my objective function should not be necessarily smooth. And we know that for gradient methods, typically they are bad when you have flat local minimum. Okay. Why is that? This is an observation that has been done by many authors, probably. The ones I know is that if you look at the stochastic gradient descent, and you write associated to the stochastic gradient descent, and you write its Fokker plan equation, the forward Kolmogorov equation, and just translating between different names of different communities. So you know your stationary state is, as you all know, the normalized e to the minus beta, the loss function. And let's assume that the loss function has a flat minima. Here, and the global minima is shallow. So there is a theorem that tells you more or less that in certain conditions, it's more likely that your descent method is going to end up on the flat local minima than on your shallow global minima. Okay, so that's one reason, probably, why to try something that doesn't use the gradient. But the others, no? If the gradient, for instance, is just too complicated to compute. Okay. So, yeah, well, just an example, probably. Well, you can cook up an example very easily with the form of a loss function with some data, with a given function, just in one dimension, and whose global minima is here. And if you try to use SED as we did in the most naive way, so we got a successful rate of only 18%. Okay? Good. I'm going to propose you, anyhow, a different perspective, which is to achieve the minimum by averaging evaluations. So let me explain the idea. And this is where the idea of consensus enters into the game. So what I'm assuming is that I'm going to follow explorers. So let's think about this. We have butterflies in Yosemite. Okay, I throw the butterflies in Yosemite. I have plenty of them. They just go around, and they are able to communicate their height. Okay, so these are my xi of t. So, and then how they interact? They interact through this average that I'm defining. I will tell you what is omega f in a sec. Omega f is some function that depends on f, on the function I want to minimize. And I'm going to take its first moment normalized with respect to omega f. So what I'm writing here is first just pure relaxation towards this average that depends on all the agents, all the butterflies. And then I put also a noise that depends on the distance towards that average, in such a way that when you are close to the average for the agents, the noise is getting smaller and smaller. And I do the isotropic, the simplest way, with the modulus of the distance. Okay, so this was in fact an idea that I started to discuss with a postdoc of mine, Stefan Martin, when he was a postdoc at Imperial College in 2016. And then He wrote a paper with the some collaborators with the numerical analysis of that. I mean, numerical experiments mainly. And we look at that from the theoretical point of view. So I want to talk about the work with Jean-Pierre Choi, Claudia Totzek, and Oliver Tse, which is essentially look at if we can prove something about this consensus-based optimization. The idea of calling it consensus-based is because I'm trying to do an average of some knowledge of the function f through this v of t here that I introduce in the evolution of each individual. Okay, advantages. We don't use gradient information at all. So we need to evaluate the function f. So, and many times. So hopefully it's not super expensive. From the more point of view of the math analysis, this will give you a stochastic process that you have a diffusion that degenerates at v of t. So you have to deal with that. And you hope to have this consensus or this kind of flock behavior, as I came from that perspective, for the location of the individuals. Okay?
Sorry, would you mind saying one more time the omega f?
That's a select. Omega f, I'm going to choose it now. So what's the omega f that I'm going to take? No surprise. I take E minus beta f. Why? Because I'm thinking of f, I'm thinking about f as the potential of a Gibbs measure. So and beta the temperature. So I take e to the minus beta f. And now, if you take e to the minus beta f, what is this average? Essentially, now let's try to get some more intuition by taking the number of agents going to infinity. I take infinite butterflies. Hopefully there are. Not so many, but yes. Anyhow, we take n to infinity. And what we see here, what we get is some kind of exact, what we get is a first moment of certain probability measure. So what's the limit I'm taking here? Of course, rho t is the limit of the empirical measure associated to this process, where I take 1/n sum of the Diracs at xi of t, assuming that this will converge towards something that I call rho t. What I'm going to get here is the first moment of the distribution rho t multiplied by e to the minus beta f. Okay? So essentially, this average, I'm taking it against this probability measure. Mu t beta, e to the minus beta f multiplied by rho. Okay. And now, when it comes into play, the idea that we have with this is in fact that we knew about the Laplace principle that is known in other communities as the, well, large deviation. But I mean, Laplace principle essentially, how I'm thinking about it and how I'm using it here is essentially to tell me that when I send the temperature to 0, which is beta to infinity, then this quantity minus 1 over beta log of this integral, it will converge to the value at the minimum of the function. Okay. As soon as I have essentially the rho t is absolutely continuous with respect to the vec, that x bar is in the support of rho t. So what I would like to think is that as beta goes to infinity, this measure is getting closer and closer to be a Dirac at the location of the minimum. Here, for the Laplace principle, I'm assuming that there is a unique minimum, and that would be the assumption on f or all the time in my talk. Okay. Good. So, how does it work? Yes.
Of course, the problem is that this convergence depends on the dimension, right?
Right. I mean, then we can talk about this. Yes. Yes. Let's get to this. Yes. So, well, I mean, this is just one example. That's the Ackley function, and we're using that with those parameters that you have. Only just 10 agents. See, I'm increasing lambda now. So just for you to see that it happens what you are expecting, you're increasing lambda, you're imposing that the rate of relaxation is faster. So that's so. And now what are the questions? Okay, so the questions. It will be very nice to know if we are able to identify for a fixed number of the agents, the n-particle distribution. I mean, the stationary n-particle distribution, sorry, the invariant measure. And if so, we are able to say that when n is getting to infinity, we get closer and closer to the Dirac delta at the x bar. Okay? And would you would like to know how fast the new Tn decay towards somehow this product of the delta Diracs as n goes to infinity, that the difference goes to 0. Okay. So far, we don't know how to answer any of these questions. But what how we have been able to do until this point is to look at the mean field limit. So the first thing what we did is, okay, let's give an initial justification if this may work. Let's derive the mean field limit equations, and let's see if the mean field limit equation does the job. What it means is from the point of view of agents, it means essentially to take n to infinity directly, take infinite agents. Can we prove that we have consensus at the minimum at the level of the mean field equation? Okay, so you write formally what's the mean field limit of this system of interacting particles. This is what you get. That's the continuous version of the system before. And what's the PDE associated to that? And then we are in business, I mean, from my point of view. Then what you get is a Fokker-Prime equation where both the drift, well, I mean, in the drift you have no mystery here, the relaxation towards the average. And here you have a noise that is degenerates when it gets to the average. Okay, so the question now is, can we prove that this Fokker-Prime equation, well, first, that the stochastic process is well defined, and can we prove that the Fokker-Prime equation does the job, say t going to infinity, under certain assumptions, it converges towards the Dirac at the minimum of the function. So that's the question that we were able to solve. So, under certain assumptions. So assumptions on f, well, obviously I'm going to assume that I have a minimum, and I'm going to assume that the minimum is positive. Yes, I mean, you just translate the function f. And I'm going to assume some local, I mean, it's always Lipschitz, locally Lipschitz, but it may grow a little bit linear at infinity. This is not important. We are optimizing anyhow. You can cut outside the interested area of optimization. And assuming that there is quadratic growth at infinity, again, the same. You can always do that by cutting at the right place. So under those assumptions, I will not enter into the details of this. One can prove that you have good solutions for this Fokker-Prime equation in sense an evolution in P2. Here, and that's a disclaimer with respect to this morning, this equation is not a gradient flow at all. Okay? Nevertheless, here you use the Wasserstein tool as a tool to prove the right estimate for the continuity I mean, for the stability to prove the system of solutions. Okay, so now we're solving here the PDE. I'm solving numerically the PDE in one dimension. Okay, just for fun if you want, just to see. I'm doing it for the Ackley function in one dimension. Ackley function is one of the typical examples in optimization. Lots of local minima, one global minima. I'm not putting the function here, I'm sorry, but you see that the important thing is that it concentrates. Okay, and it concentrates at the right place. Okay, so some numerical justification for the mean field limit. Again, the mean-field limit, I derive it formally. Theoretically, it's more complicated than mean-field limit in this case, and I will not enter into that if somebody is interested in it, but it's not a direct application of the standard theorems for one, yeah. So in fact, it would be nice to also get that kind of result at the theoretical level. But what do we look at is, let's take the empirical measure. The empirical measure is a random measure in this case because of the noise. So we did experiments to check what happens with the expectation of the random variable, which is the Wasserstein distance between rho Tn and the Dirac at the minimum, and also for the variance. So, I mean, this is encouraging somehow. This is number of particles we were using. By increasing the number of particles, you see that the variance decreases. Okay, so that's somehow was the numerical experiment that we did in order to make us happy that maybe there was a theorem behind that we had to work. Okay, so as I'm telling you, the goal is to show that rho t converges to the Dirac at a point. And in fact, what I'm gonna give you ideas on how we did the proof. I'm gonna enter into the full detail. What we prove is in fact that rho t converges to a Dirac at a point, and that by choosing the parameters that we have, lambda, beta, sigma, mainly beta large enough, which means temperature small enough, then as t goes to infinity, the x bar converges to the Dirac as t goes to infinity, and the x hat, sorry, is in a ball of radius epsilon of the minimum. And you can get the epsilon as small as you want by taking the beta as large as you want. We don't get an explicit rate. Okay, we just get a result that tells me that for beta large enough, I can get the point to be as close as I want to the minimum. Yes.
Clarify. So in this limit towards delta, beta is going to infinity.
Yeah.
Beta is going to infinity along the.
No. We are not moving beta. This is beta fixed.
And even with fixed beta, it goes to Dirac delta.
Yes.
Okay. Thanks.
That's the point. The question is that the beta will then use it to be close to where we want. Yes, that's right.
Can you write the explicit statement? It's going to be some mean of some Gibbs measure that you're converging to, right? The x hat?
No, I cannot give it explicitly. No, not at all. It's an argument totally, yeah. No, it's not constructive. No, I don't know.
And did you run some experiments if you actually just if beta equals infinity, like your PT is the minimum of the current point, of the current set of points?
Yeah, it would take beta large enough.
So it still works?
Yes, I mean, beta infinity, we don't have to, no, we cannot take beta infinity
So
directly.
you can just say BT is the argument.
The question, yeah, I see what you mean. Now that has more issues. Yeah, no, no, with the exact value, no. That case I cannot make it. Yeah, sure. No, the x hat is going to be, in fact, the limit of the average as t goes to infinity. This is what is going to be in the proof. The x hat, and what I can say is that the x hat is going to be as close as you want to the minimum if beta is large. Is it clearer now?
Yeah, but you don't know that x hat is the mean of some explicit
No. We don't know anything else than this. It's just the limit of the average, and that that limit is if we choose the beta large is close. Okay. Okay, so how it goes, and just to give you a hint of the proof, because I think it also it gives the idea how it works. So I mean, we compute the evolution of the variance of rho t. So just the second moment around the mean of rho t, and then you get this expression. And I want you to make emphasis. I want to make emphasis on 2 points here: the dimensional dependence here, and here we get the average with respect to the Gibbs, e to the minus beta f rho. Okay, so we had to relate this kind of quantity with that with the variance if we want to do something here. And let's assume that we are already very close. I mean, just to give you an idea, let's assume that we are already very close to the minimum. Okay, so somehow that the f is in between f sub f, which means the minimum, and the sup of f, and let's assume that that difference is small. Okay, so then you can just bound by kind of Jensen this quantity in terms of the variance by this quantity. Okay, and then what you see is that if you allow, I mean, let me call this, I mean, it's not the same epsilon as before, but let me call this quantity epsilon. I should have called it differently. So if you take lambda larger than d sigma squared multiplied by that quantity, you are going to get that the variance decays exponentially fast. Okay? Which is already a good indication. It goes to 0, as t goes to infinity. This is what you want. Okay. So if lambda is larger than d sigma squared times something, then this should tell you that the variance goes to 0. But in fact, this implies that the average that I'm using for the method, and the expectation of rho also converge towards each other as t goes to infinity. Okay, and I'm going to show you a little bit on that. And I need, in order to do that, I need more assumptions. So as I told you before, I assume always that the influence is positive. I'm going to assume now smoothness. And this is where it enters in the proof. I need smoothness, second derivatives of f. And since in RD, I need this. But again, these assumptions, if we were to use it in practice, you can always assume it because you cut outside a big ball. And this is not important. The only important thing, the important thing is the smoothness. Okay, so in fact, I don't want to bother too much with all the constants here. But if you choose now the lambda, the sigma, in a way, and the beta, in a way that you have these relations with the c's that appear here, and with the variance initially, and with the L1 the L1 norm of e to the minus beta f with respect to rho naught initially, they enter, that's the initial values that enter into this, then you can get, as I said, in general, that the variance decays exponentially fast. This is more general than the previous one, in which I was saying that it was local. So one can do that more globally, and still you have that the variance decays exponentially. Okay, so that's the core of the core lemma to prove. Once you have that, you look at the evolution of the expectation of rho is given by that quantity, and this quantity, because of the variance decays exponentially fast, is iterable in time. So this means that this expectation has a limit. So that's where I'm getting that I have a limit of this average as t goes to infinity. So once I have a limit, the question is, you have to really prove that that quantity then converges to e to the minus beta f at the delta Dirac. Sorry about the hat, and now it's tilde. Okay, the limit. Now we have achieved the consensus. Now we have done that under certain assumptions on the choice of the parameters. Now is where it enters to choose beta. And beta is where we use the Laplace. So for doing Laplace, and one has to be careful with this. And it enters also the value initially. That is where the initial distribution plays a role. So anyhow, with the Laplace principle plus the evolution of that quantity, and I will not enter into details, you can show that then you will have this, well, you will have this kind of control on this quantity. And precisely this is what Laplace tells you, is that you can choose beta large enough in such a way that this difference towards the minimum is small. So this together with that implies what I said, that the x tilde here is as close as I want by choosing beta large enough to the x pi. Okay, just to give you the steps without entering into details. So one has to do also a little bit more cumbersome argument at the end with the Laplace principle. So this tells you then the method works with n equals infinity, but with no rate of decay. I don't have any rate of decay here. Okay, let me now, is it clear up to this point, more or less? Okay, now let me give you some variants. So another variant that we have done, well, yeah, I'm just reminding you again the same thing, and just to give you another well, variants that people have done. So one variant, of course, is to avoid very much in the spirit of the positive part of the energy this morning for Katie, why to go in directions where the loss function is increasing. So you can always put a cutoff when the difference of the values goes in the wrong direction and makes it faster. But that's not the point I want to make. Here, I came back to the finite dimensional case, to the discrete case, in a sense. And now I want to make the point that, remember that I had to choose the lambda of order the dimension for my theorem to be applicable. So lambda had to be something like d times sigma squared, something like that. So obviously we were not happy with that. Essentially, you want to use that for machine learning problems. It's not going to be the case. Okay, so can we do some variant of it? So, so let me show you the first improvement that we did in order to avoid the dimensionality, and then also in terms of efficiency of the numerical method. This part of the work, I did it in collaboration with Xijin, Lei Li, and Yuhua Yu. Yuhua is also participating in the program, but she will be here tomorrow, okay? And it will help also in the group, in the seminar group that we have. Okay, so what's the first improvement that we have done? Choose a different type of noise. And I will explain you in a second why. We did an isotropic noise. So what we did, what we thought is, why don't we do relaxations again? In the noise term, we put degeneracy to go in the direction of the average. Now the notation changed, okay? Sorry for that. X bar star is the average that I was doing with the e to the minus beta f. So I do that, but instead of doing with the modulus, I'm going to do it with independent Brownian motions in each of the components, so component-wise. Okay? Why I do this? Well, intuitively, you could say that now this will allow to explore more the dimension in each dimension with different rates. But the fact is that we thought in terms of the estimate. So let me show you in the first CBO model, this was essentially the estimate that enters. So, I mean, just to simplify everything, this has to be the average. I mean, sorry, the average. I was computing here with the average, but let's do it just with a constant to see the dependence on dimension. So if we repeat with a constant, what happens with the decay of this when you have just a constant and not the average? So, well, for each dimension you have that. So you do the algebra, Ito's formula, take expectations, sum of the dimensions. I mean, you can do that with PDEs too, just by writing PDE, compute them a moment, and so on. You end up in this. And that's precisely where the dimension enters. When you add here, you are adding these, in each component, and then you get minus 2 lambda plus sigma squared d. So you need that kind of condition. Okay? So now what we did here was essentially by doing it component-wise, the big difference is that now when you sum, you recover now the full expectation here without the dimension. So now the condition that you need doesn't depend on dimension. Okay. Well, if you go to the theorem that we proved before, and you just change this fact, the proof applies equally well. Okay, modulo some little lemma that we had to add. But essentially the same proof gives you also the convergence of this guy in the same kind of result. But now there is no dimension dependent. Okay, what about the cost of the numerical method? Yes, well, I mean, just to write again, the mean field limit of this one will correspond to this kind of McKean-Blasov equation, like McKean-Blasov-like equation. You can write again the PDE you want. And essentially, the theorem at the end, we made it a little bit more explicit in terms of the initial value of the loss function and the dependence on beta. So essentially, you can take beta large enough under those conditions in such a way that you are at a distance 1 over beta. Okay. Well, I mean, here you will see the dependence on the initial value and the dependence on beta. But for the numerical method, as I was saying before, we tried also to improve it. Why? Because you're taking the average. It's an interactive particle system. So if you look at the cost that you have in terms of the number of particles, each evaluation, I mean, if you do some kind of implicit something or explicit Euler or whatever, anyhow, you will have a order of n squared to compute because you have these double sums. So we also thought in terms of improving this, and I'm not going to discuss too much here, but these comes from a recent series of papers of Shijin and collaborators that started with a paper of Shijin, Lei Li, and Jianguo Liu. They introduced the so-called random batch method for interacting particle systems, and they propose and they gave quantitative bounds also for this interacting particle system on the error that you commit by doing this kind of procedure. Here we didn't study the error that we commit, but let me just explain you what is this random batch method. Almost the words say what it is. So let's count what we need to do. Okay, so we have to calculate the value of a function I want to minimize. And typically in machine learning is something like that. So you will need this order of the number of data that you have, kind of. The weighted average that you need to do is of order capital N, number of particles. So the order of computation is going to be like that. Good. So might be very heavy, especially if you are in with lots of data here, or with many particles. That is where we know that it's becoming better than the model. Okay, so what we do instead is we generate m particles initially, and at each step, what we do is to update only m particles out of those n. And at the level of the evaluation of L, again, you choose a batch, a group of particles in which you're going to use for both the evaluation and the sums here. Okay, and you choose them randomly at each iteration. Okay, that becomes of order m because that's the size of the small batch. The same thing here as I said, so it's becoming little om. So then you make it order 1. Okay. For the random batch method, as I said, I don't have estimates on the error. They have done estimates on the error, the random batch method for basic McKean-Blasov equation. It would be, it's a very interesting open problem. Okay. It would be nice because it's a way of making efficient all these kind of things. Anyhow, this is what we did.
I used order 1 here. I'm confused.
Yeah, no, at the end of the day, capital M and little m are much smaller. So essentially, this little m times capital M is like order 1. This is what I mean by that. You see, because that could be, I don't know, you can make the update of only 2, say. Okay. Good. So, well, I mean, we did the same example as with the stochastic gradient descent for that particular case with the flat, that the stochastic gradient descent in the simplest form wasn't working too well. I'm sure you can make it much better than that by doing any of the other variations and improvements. But with this method, well, you get it, success rate 98% with 100 particles and with the batch being 20. Okay, so you update only 20 of them in each iteration. Okay, so that's all what I wanted to say on the optimization side. Yes.
Is in 1 dimension.
I mean, this sample is in 1 dimension. I was explaining in general. I mean, it's just a sample. The simulation, sure. Is this function just in 1 dimension? We did in the paper.
So if you compare
Real.
this with simulated and living,
We didn't do a complete comparison with other things because, yeah, you know. No, we didn't do that study. If you're interested in a more realistic example, we did that, and I had it in a slide that I have at the end. I can show it now or show it at the end to you. But we did like MNIST data set, a real, yeah, typical example for this kind of neural networks. And we computed the parameters of a ReLU, 7,400 parameters, and essentially with the same kind of idea. Okay.
In those larger examples, how were you choosing?
Oh, very small, because if not, yeah, M, very small, because if not, it's not feasible. I can show you the results later if you're interested in on this. Is it fine? Yeah.
So what you plot here is that expectation by taking the random variable on the normal.
What do you mean?
Because Lx is defined based on the random variable x hat. So each time we do the evaluation, it could.
Yes, so we just generated this by with certain value of n that I don't remember now.
So it's more like expectation.
Yes. Okay, so how much do I have left? Okay, so in the last part, I wanted just to briefly mention about ideas that we have done very recently. This is just a work we finished before summer, so in July, in collaboration with Franca Hoffman, that is going to be also in the program, Andrew Stewart, and Urban Baez. Because the question came naturally, because Andrew has been working many years on using ensemble Kalman filters, ensemble Kalman inversion, which are derivative-free algorithms to do inversion problems. So his question was, can one adapt your ideas to produce something of that sort that does sampling for Bayesian inference? That was his question. So we started to work on that. The previous time I was in California, which was the last trip I did internationally before the pandemic. Okay, so, and I'm going to tell you a little bit about that. So let me see if we will, I mean, this one, it can be discussed in the group if you're interested in. I'm sure Franca will be very happy to do that. Okay, so let me set up the inverse problem that we want to solve, okay? So I know that it's a bit changing gears, but you will see the connection and the idea, but I need to set up now a little bit of notation for that. So here, theta are the parameters, and G is what is called usually the forward map. You have the data, and the data are given by the Y's, and then you have some noise in the data. Okay, so essentially what you want to calibrate are the parameters. And here again, we will be thinking in terms of derivatives of G are not available, and G even is expensive to evaluate. So we want to do the minimal evaluations we can also on G. Okay, so let's formulate that as an optimization problem. First, you can think in terms of finding the best choice of the parameters, theta star, by minimizing this function. Okay, so just the difference between the data and the forward map, G of theta, in just Euclidean norm, and then plus a term that it comes from the noise. Okay, so essentially, and probably I don't have to mention many of this to many people in the room. They know much more than me for this. So in the Bayesian approach, what you are essentially doing is these assumptions. You have a prior distribution for the parameters that you assume is normal with some variance, covariance metrics. The likelihood is what we are assuming that we have the noise on the between the data and the map with respect to the parameters. And then the posterior, you just compute it with Bayes' theorem. You just write that the probability of theta condition 2y is given by that, and then is proportional to this product. That's how you get that is exponentially to the minus beta f of theta. Okay, good. So the question now will be, can we generate approximate samples from e to the minus f? Okay, or I mean, you can give the maximum probability point by finding the minimizer of f. That could be also a, if you think in terms of optimization. Well, so we call it consensus-based sampling, the method. Let me explain you the idea here. Again, it's very similar to what the intuition is very similar to what I was explaining you. We want to compute averages of the rho multiplied by the Gibbs, e to the minus beta f. So we take this as the empirical, the probability measures, rho times e to the minus beta f normalized. And we use now its mean, as before, different notation again, and its variance. Okay? And well, just for formulas that may appear later, if I just use without the beta, means that m of mu is the mean of the measure mu, and c of mu is the covariance matrix of the probability measure mu. Okay, so the discrete version, the McKean kind of difference equations that we use is again a relaxation towards the average as before, as I used for the optimization, but now the noise, I'm using the variance itself with respect to, again, this probability measure. So I'm changing the noise, I'm modulating the noise, if you want, with suitable parameters with the covariance metrics. Okay, I had to tell you that this is not the way in which I thought about it. I started thinking about the PD, and then we wrote the discrete version of it. Also because Andrew asked me, no, I want the discrete version of it. Okay, fine, let's find a discrete version of it. So for him, it's much better to think in these terms. But okay. So you see, again, the advantage of this is that there is no derivative. Good. Let's write the continuous version that everybody is on the same page, no matter the community where you come. Now I'm writing the continuous version as an SD. So what I'm telling you is that I'm taking the relaxation towards the average with respect to the e to the minus beta f rho. And the covariance matrix, it has a factor, a scaling factor, I will discuss in a sec, 1 over lambda times the covariance.
Sorry,
Yes.
So what's the motivation for not using the difference between theta and the mean in front of the noise, but using the covariance
The
matrix?
theta and the mean respect for the noise. To have the, I mean, the intuition we thought is because in any case, we were using before the average towards the mean. So we were not taking into account the expansion of the distribution, or let's say that the asymmetry in different directions of a Gaussian, like you have a Gaussian with one value which is matches with one of the direction, which is much more squeezed than the other. You see what I mean?
You want to avoid the collapse, basically.
Yeah, and also that's at the point. This lambda is to avoid the collapse. I'm gonna get to that in a second. But the choice of this is independent of the lambda, because we can use also, I mean, what he's asking about the collapse is, how can I avoid now that this goes again to a Dirac? So it's this lambda that plays the role for that. Okay. So that's I mean, associated to the SDE, you can write the PDE. I mean, it will be written in a second. I don't know why I didn't put it just after that. Okay, so let me just to give notations. And if I go back to the discrete version, I have two parameters, beta and this alpha here. Okay. The alpha, to take the continuous version, what I did is to think about alpha as e to the minus lambda t, and then take lambda t going to 0. And that is how you get this one. Okay. And so what are the two methods that you can get out of this? So if you choose lambda equals 1, and this goes in the direction of what Leon was asking me, this is what is the optimization mode, in the sense that you will see that then this case we get again the concentration to a Dirac. While if you choose lambda depending on the temperature, then you avoid the collapse, and then you converge towards something. Well, that's what we prove in some of the cases. Okay, the first thing is, in fact, let me just explain you that. Fixed points, stationary states are independent of alpha, and in fact, they are Gaussians. You can compute them in particular cases, even explicitly. So I will come back to that. They are always Gaussians anyhow, but also at the continuous level, this is the evolution of the mean and the variance is with respect to the mean and the variance of the gifts. So you have to work to see what happens with this as t goes to infinity. But just to give you an example, if you choose the simplest one, so you take the linear forward map. So essentially your f is quadratic with a matrix there. So you can compute all of this explicitly. Your stationary state is a Gaussian with this mean and this covariance matrix. So you see now the role of the lambda. If I choose the lambda well enough in terms of beta, I avoid the collapse. I can choose lambda equal 1, I will get the collapse to a Dirac. And yes, with this, I'm getting out of almost. So yeah, well, I promised that I would like to write the PD. So here it is. There's the PD. Ah, no, I don't have it here. Oh, the PD is there. And let me mention that at the continuum time dynamics, so we are starting essentially with this kind of method. So we have studied a lot the decay rate of the discrete versions, because this is what Andrew Stewart was originally more interested in it. But we haven't looked at that much about long time asymptotics of the PD and rates of convergence of the PD and other properties, just because we started to solve one question at a time. But yes, to finish, probably I want to finish with that you see it in action. So again, if you use it in optimization mode, that's either the Ackley function or the restringing function, two typical examples in optimization with lots of local minima. So here, it works. Perfect. So you see how nicely it works in terms of optimization too. So essentially, here the difference between the two is the alpha. That one is closer to be alpha equals 0. That is closer to be the continuum version, the alpha close to 1. Yeah, just for you to say it, but of course there are plenty of discussions in the preprint, and we can discuss that about the decay rates and so on. For sampling, we use this as a one-dimensional problem for sampling. So what you do is to solve that elliptic van der Waals problem in one dimension, where your data are just evaluations of the function that known at 2 points. So it's a very typical test case that Andrew was using for a while. And let me show you just one simulation. So this is the case of sampling when lambda is less than 1. So what you get, again, your agents, your butterflies are approaching the posterior. And yeah, well, they're getting better and better and better. And getting closer to the posterior, this is what you want. Of course, this is with beta fix. We never change beta. And there are many improvements that we do also in the paper by changing the beta and at the discrete level and analyzing that. So that gives you an idea of what we are doing in that. And thank you.
So any questions?
Yeah, so thanks, José, for this very interesting talk. Have you considered choosing beta time dependent, for which is proportional to time, such that you get closer to the real minimum as time proceeds?
That's a very good idea. I mean, that's like the cooling schedule for the simulated annealing. We haven't studied that, and that's a very natural question. I agree.
So since I have you, I have this question about how this particular choice of the equation, let's talk about the optimization one first.
Okay, that's fine.
Came to be, right? So okay, you have this consensus and you want to have a term that basically says I want them to collapse. So I'm going to actually have like some, the variance of this thing to actually collapse at some point. And you just, all these terms look natural. And I wanted to know if you investigated other terms. Is there any hope to actually have a similar behavior where you have a term that just, where the variance collapses that you put in front of your ground motion that
Yes.
would be a gradient flow in Wasserstein, for example. So somehow, like when you write the Fokker-Planck equation, there's this weird term that I wonder if you can just try to play around and see if you could actually modify this variance term so that it would actually be some gradient flow and have some velocities in there.
I have to say that no, we haven't done that yet. But what I can say is we look at, for instance, in the case of the isotropic noise, it's a very natural question because I mean you can invent whatever you want. At the end of the day, it's your objective. The important thing here, there is no physics that you have to follow. I totally agree. So if you put for instance, we investigated in the noise term instead of modulus period, modulus to a power, and didn't change that much the results, and we didn't see any advantage. In fact, it was making it more difficult from the math viewpoint if the power was a bit larger than, I remember if it's 2, I think. So I mean, we haven't. No, I agree with you. We haven't explored all these things, so I'm happy to discuss. Yeah, we haven't explored. I mean, this is as much as we know.
So any other questions?
Just out of curiosity, how did you prove existence to this Fokker-Planck equation?
It's just a fixed point argument on the paths in W2. It's an uninspiring result like that.
Just do it by hand.
By hand, a priori estimates on moments, and then fixed point at the level of the SD. That there is where this power enters that makes our life difficult.
Problems that you are trying to solve here, we know are in full generality, they're computationally hard, they're intractable. So what is the hope here? Is there a hope of finding some subclass that is tractable, like we can solve, like what is the best we can hope to prove?
Yeah. That goes in the direction of the efficiency of the algorithm that I was discussing at some point with the random batch and so on. That is what it makes it feasible for a large dimensional problem. Okay, but for that we don't have a theory underpinning any kind of error estimate that we do. But I mean the results, as we were saying before. I mean I had them over here in a okay that. So so this is the MNIST data set with two-layer neural network. Your dimension is 7,290. We use M 100 points. M equals 10 is the batch. So we update 10 randomly chosen particles at each iteration. And well, we were looking at this typical graph that appears in many papers in terms of what is called number of epochs, and compare the different. These are different choices of the number of. One of them is exactly that one, and the other two are other choices of N and M. So you can do that. Would you get? You can compare to the success rate. That's the success rate, the accuracy on the test data. So it's just, you can use it, but again, we haven't explored that much these aspects.
How much you can even hope to prove?
I mean, you could run it on some, I mean, it's a zeroth order thing, right? So we don't have that many tools available for zeroth order optimization. So you could even try to prove stuff for like convex optimization, right? And with zeroth order rather than doing the 2-point gradient for it.
In fact, that's also a thing that I'm interested in learning. What are the interesting problems from your point of view, guys?
Yeah, if you have more questions, maybe you could ask the speaker during the time. So thank you for the very nice talk. And thank the speaker.
Thanks, enjoyed the talk.
No problem. No worries. I mean, I didn't.
Can I just look at